All right, good afternoon, everyone. And so today we'll just continue where we left off from last time. Remember, the idea of this section is to introduce you to some methods that you can apply to do data science or data analysis. Kasi importante na, I think one of the criticisms that at least mathematicians have about data science is it's more of a black box mentality or a black box paradigm or aspect into data science because most methods nowadays, and even ganito yung ginagawa ng mga practitioners, ay meron ka lang isang black box representing your process. So meron ka dyang black box representing your processes. Okay. And then what usually most practitioners do, especially those beginning practitioners, what they do is to feed data into uh into the block box, and then they let the block box do its thing without even tinkering around it or looking at how it works. So meron ka lang bulk na data. Of course, probably here you do some pre-processing, like normalizing your data or screening out some outliers para maganda yung papasok dun sa black box. But essentially, ito yung nangyayari. Meron kang data, ipiprocess mo siya, tapos i-input natin siya sa isang black box. And these black boxes, ito na yung mga methods that were tested. At sila na yung mga gumana before. And what we expect is for this black box to give us some outputs. Okay? So parang ganon, yung parang sort of simplified description of the pipeline in doing machine learning, for instance, na kaya nga machine learning yung tawag natin eh. We want the machine to do the learning by its own. So ibig sabihin, hindi na natin siya papakialaman. If i-feed lang natin siya ng data, siya na yung bahalang kumuha ng relationships and insights from those data, tas bibigay niya na lang sa atin yung outputs. Okay? But this course is titled Mathematical Data Science. So gusto nating medyo dumistansya ng kaunti dun sa true blood data science thing. This is mathematical data science because our idea is to sort of, number one, understand what happens in the black box. Though hindi nga ito yung standard na ginagawa ng mga data analyst or data scientist, because the idea sila yung nag-pre-process, sila yung nag-organize ang data before inputting them into the black box. Pero since we are trying to give data science a more mathematical flavor to it, tinitingnan natin ano yung pwede nating magawa dun sa black box. So, and then part of doing that is to analyze what are the processes or what are the tools na pwede nating ilagay dun sa ating black box. Because I think this is a nice area for development in data science kasi nga usually kailangan mo ng napakalaking data para mag-train ng isang model, alright? Para makuha niya or para magkaroon siya ng maayos na machine learning. But the idea is how much data should be inputted into the black box. Kung meron kang data, ilang percentage dapat yung gagamit mong testing data, tapos ilan yung valid training data. So parang wala siyang theoretical foundation. And we are just relying on heuristic estimations at ano yung mga nag-work before. Pero at this level, gusto nating intindihin ano yung mga processes na nangyayari doon sa loob ng black box para pwede nating i-optimize yung process. And I think that's the difference between doing mathematical data science from true blood data science. Kasi rito, titingnan natin paano natin ma-improve yung black box para dun sa mga non-mathematics major or specialist. Ano? And part of this is that this black box or these black boxes usually employ large linear systems. And lalo na sa parameter estimation o sa pag-extract ng useful information for say clustering or classifying data. So merong isang malaking linear system na nandun sa black box. And that's the focus of the first or this section. We want to look at how to efficiently handle these linear systems. That's why meron tayong numerical linear algebra na section dito sa course na to. And we have established a sort of an outline na gagamitin natin for this section. Though siguro kailangan ko mag-extend ng 1 or 2 more meetings to cover everything, but I think we have the liberty to do that. So simulan natin sa linear systems. Now, if we assume that we have a square system, meaning we have the system AX equals B, where A is an n by n matrix. Okay, that means X and B are both they are both n by 1 vectors, right? So n by n dapat n by 1 tapos n by 1 din yung kabila, all right? And then our idea or our question last time is how do we efficiently solve this linear system? Sabi natin, alam natin yung naive solution o yung tinatawag natin classical reconstruction. Kunin lang natin yung A inverse. But we have mentioned that computing A inverse is a very computationally expensive and unstable thing. So mahirap hanapan ng A inverse lalo na hindi naman lahat ng matrices ay may mga inverses. So ang tinitingnan natin ay paano natin to gagawin. Sa linear algebra, probably natuto na kayo nung Gaussian elimination or probably even in your high school or college algebra, you learned how to do Gaussian elimination. Yung nag-add tayo or nag-multiply tayo ng isang equation by a constant so that when we add the answer to another equation in the system, one of the variables will be eliminated na parang every iteration or every pass of the elimination process nababawasan yung mga variables. And actually, instead of matrix inversion, even though the two processes are or can be shown mathematically equivalent, mas preferred yung Gaussian elimination method kaysa dun sa ginagawa natin na matrix inversion. Kasi nga mas mura yung computational expense na kailangan nating gastusin to do Gaussian elimination. However, Gaussian elimination is not most efficient way to do calculations. Lalo na kung iterative yung pagkuha ng right-hand side. Meaning, there are lots of processes like in machine learning. You do you feed this data, pero yung matrix A ay hindi naman nababago. All right? So we just have different say data vectors B. Meron kang B upper 1, B upper 2, B upper 5, and so on. Tapos isusolve mo lang yung same linear system to compare the parameters that you get. And if those parameters that you get converges to another vector of parameters, then you can say na natuto ng maayos yung aking machine learning algorithm using a varied set of data. All right? Kasi parang yun nangyayari. So again, you can imagine X to be your undetermined coefficients dun sa model na gusto mong hanapin, parameters. Tapos yung relationship naman with the parameters and the supposed governing principle ay hindi naman nababago yon, right? So si A ay fixed matrix. Tapos gusto mo lang i-fit ano dapat yung mga parameters na mag-undergo nung aking governing equation or governing principle para makuha ko yung data or mamimic yung data sa real life. Of course, halimbawa, day 1, nag-experiment ka, nakakuha ka ng B upper 1. So, isosolve mo tong system na to, makukuha ka ng solution X upper 1. Alright? Pero kinabukasan, nakakuha ka ng another set of data and you want to see if parehas pa rin ba yung parameters na makukuha ko under the same governing principle, pero iba na yung data. It's a brand new, fresh set of data. And during these times na napakadali ng access sa data or ang daling mag-simulate ng data, talagang ganito na yung nangyayari. Multi-step na yung nagiging training. And then makakuha ka na, isosolve mo itong bagong linear system na to. You get another set of parameters and you do this say 100 of times or 1,000 times. Titingnan mo ngayon, nagko-converge ba to a certain vector yung vector X. Alright? So hindi siya ganun kadaling i-implement at hindi na ganun ka-efficient yung Gaussian elimination, kaya tayo tumitingin ng matrix factorization methods. Because what we do is we factorize or we decompose the matrix A into 2 or more factors na magiging mas efficient either yung inversion o yung overall elimination process. Okay? Tapos sinimulan natin siya last time dun sa Gaussian elimination, and the idea here, not Gaussian elimination, but sa LU factorization. And I introduced you to the concept of elementary matrices. All right? So, ang idea natin na nakuha last time ay, ganito pala yun. Kaya kong makuha yung LU factorization by retracing how we do the elementary row operations dun sa Gaussian elimination pass. So, what we do is, halimbawa, meron ako matrix A. Ito yung coefficient matrix na given. I will perform to this a set of elementary row operations. Tawagin kong operation 1, operation 2, operation 3 in the first pass. And then after this, we get the matrix, say, let's call it A upper 1. Para ito yung output ng elementary row operations in the first round. And then another round of elementary row operations that can be interchanged. Pwede nating gawin sa isang pass o isang pasada nung nung um, nung ERO operations, right? Or nung ano bang tawag natin dito? Gaussian elimination nga bang tawag natin dito sa 120? Pero ito yung steps dun sa row reduction, no? Sa row reduction process. So you have another set of elementary row operations that you will perform on the second pass. So siguro tawagin nating O4 at saka O5 yung mga operations na yon. Makakuha tayo ng another matrix A upper 2 on the second elimination pass. And then we do this until we get a nice form. And the form that we want in the Gaussian elimination process ay magkaroon tayo ng upper triangular matrix. So magkakaroon tayo dito ng bunch of elementary row operations. Now, ang goal ko ay makakuha ng LU factorization. Of course, there are several developments or iba't ibang paraan para makompute yung LU factorization, but this is what I prefer, especially when teaching higher mathematics courses. Kasi hindi tayo computational eh. Magandang itali yung konsepto ng elementary row operations na ito pala ay kayang dahil yung operations na yan ay linear, kaya ko siyang i-represent by a matrix, right? Ito yung natutunan nyo sa linear algebra. Na pagka meron kang linear transformation, kaya mo lagi yung i-transform into a matrix operation. Alright? So ganun din sa EROs, right? So idea here is each of the elementary row operations always correspond to an elementary matrix. And that elementary matrix is the matrix form by performing the said elementary row operation to the identity matrix. Yun yung mga elementary matrices natin na tinatawag. So operation O1, be it an interchange of rows or a row translation or a row scaling, will have a corresponding elementary row operation to it. Say, tawagin natin siyang E1, right? And then to perform the same action as O1 on A, kailangan ko lang i-pre-multiply si matrix A nung elementary matrix corresponding to operation 1. Ito yung ginawa natin last time, ano? So si O1, gagawin ko lang siya sa identity matrix, makuha ko yung elementary matrix. And then to mimic what O1 did to the given matrix A, all right? Ang gagawin ko lang, ipe-pre-multiply ko lang si matrix A ng elementary matrix E1. Alright? So makukuha ko yung effect ng ginawa ko yung operation O1 kay matrix A. And the answer should be this matrix product E1 until A. And then we do this for all of the operations, right? Hanggang makarating tayo dun sa upper triangular matrix. So pwedeng meron ka ritong E2, E3, E4, and say it took you, say, M operations to get here. All right? So, pero medyo malapit na to sa LU factorization kasi meron na tayong U. All right? Gusto ko kasing masulat si A ay equal sa L times L times a matrix U. L is lower triangular, U is upper triangular. Okay? Pero at least ngayon, meron na tayong U. Ano na lamang si L? Right? Now, I am hoping na yung LU factorization na to ay pwede kong magawa this way. I am hoping that this product here is invertible. Sana invertible siya. So, kung invertible siya, kaya pwede kong i-apply yung inverse niya to both sides and get, A equals EM until E1 inverse, i-multiply ko lang kay U. Alright? So remember, ang goal natin ay A equals LU. Now, another prayer that I have is that invertible to, sana ito ay maging lower triangular para makuha na natin yung LU decomposition. Yun lang pala, para makuha yung LU decomposition, pag nag-work yung mga prayers ko, or pag natupad yung mga prayers ko, yung lower triangular matrix lang pala ay product ng mga inverse ng product ng mga elementary matrices. Pero in the right order, para makuha ko yung L dun sa LU factorization, right? And I hope that that is a lower triangular matrix. Then I guess we have several theorems here to tell us na, okay, pwedeng mag-work yung sinasabi ko kanina. Pero I should mention this now na we are limiting our discussion first to those matrices that can be transformed via elementary row operations to an upper triangular matrix na hindi kailangan ng row interchanges. So what I'm saying is, etong dinidiscuss natin na methods ay mag-work siya kapag wala tayong ginawang interchange of rows dun sa row reduction. Makikita nyo, sabihin ko mamaya kung bakit ayaw natin na may nag-i-interchange na rows. Kasi kailan nga ba tayo nag-i-interchange ng rows pag nagre-reduced row echelon form? Tandaan nyo ba? Linear algebra. Alam ko may mga algebraists dito sa group eh. Magtatawag na ba ako? So, kailan tayo napipilitang mag-row interchange kapag nagano tayo? Pag nagre-reduced row echelon form. Tandaan nyo ba? Nina? Usually, nag-i-interchange tayo ng rows kapag yung leading entry niya ay, di ba dapat yung leading entry sa ith row ay dapat hindi mauuna dun sa leading entry ng i-1 at mga nauuna pang row sa kanya. So, minsan na-foresight talaga na pagpalitin yung kanilang positions, right? So now, in this discussion or in this module, I am assuming that I don't need to do row interchanges. Kasi hindi naman laging required na mag-row interchange ka. So, ang inassume ko lang ay, ito yung mga cases na kailangan lang natin yung row translators. Okay? Kasi pagka hindi lang row translators yung kailangan mo at kinailangan mo na ng row interchange, hindi na LU factorization yung makukuha mo. Pwedeng PA equals LU factorization na kasi dapat may permutation matrix tayo na ipe-precondition yung input matrix A. But that's a more detailed side of this factorization method. So for simplicity, tingnan muna natin yung mga kaso na hindi ko na kailangan ng pre-multiplication. Hindi ko na kailangan ng row interchanges. So kaya ngayon, yan. Ayun lang yung titingnan natin, yung mga hindi kailangan ng row interchanges. At kung makikita nyo, dito sa dito sa ating ginagawa, ang nagiging bulk dito sa aking approach, ang nagiging bulk ng work ay yung yung pagko-compute ng corresponding elementary row operation para sa bawat isang pagko-compute ng elementary matrix para sa bawat isang elementary row operation, pag-arrange sa kanila sa isang matrix multiplication equation, tapos later yung inversion. Okay? So titingnan natin yung mga shortcuts. Dahil ngayon, limited na tayo dun sa pagko-consider ng mga matrices na kaya nating i-reduce into an upper triangular matrix using only row translations. Pwede ko nang tingnan ano yung itsura ng elementary matrix in general kapag naggagawa ako ng row translation. Alright? So, halimbawa, ito yung row translation operation mo. You want to replace the kth row of the given matrix by the kth row plus a multiple of the lth row. Okay? So, titingnan natin in general, ano yung itsura ng elementary matrix na yan para madali nyong ma-program ito. Halimbawa, magsusulat na kayo ng program for LU factorization para mas madali nyong makuha yung kasi mahirap ituro yung ginagawa natin na kakapain ko lang ano dapat yung i-multiply ko and so on. Madali siyang i-figure out by hand. Pero paano mo siya i-encode sa isang machine, right? So you have to determine ano dapat yung gagawin mong row operation at ano yung itsura ng actual matrix na makukuha natin. Now, this remark is telling me that the row operations that we'll be using will all have diagonal entries 1. Tapos meron na lang siyang isang non-zero entry dun sa ibang position or at least exactly one non-zero entry. Kasi yun yung magiging itsura ng elementary row matrix. So whenever we want to get the elementary matrix corresponding to the elementary row operation suggested by this this operation, ano? So nagiging itsura lang nung elementary matrix ay ito. Right? Tingnan natin kung bakit ganyan yung itsura ng elementary matrix para sa row translators. So, kailangan ko siyang i-perform sa identity matrix. So, start ako sa identity matrix. 1, 1, 1, 1 siya lahat. Tapos 0. Tapos pag ginawa ko, yung kth row ay pinalitan ko ng kth row plus the lth row times c. So, halimbawa, ito yung kth row. Tapos, halimbawa, ito yung lth row lang kunwari. Okay. Pag pinerform ko itong elementary row operation na to, ano yung mga mangyayari? Ito ay magiging, hindi mababago yung mga nasa diagonal. Puro 1 pa rin yan. Okay. Kasi mangyayari lang, si lth row mamumultiply ng c. Pero ito ay 0. So 0 times c ay 0 plus 1. So 1 pa rin yung nandun sa kth row. Ang mababago lang actually sa kanya ay yung nandito. Kasi ito lang yung mamumultiply ng C, idadagdag ko siya sa kth row, so magkakaroon ako dito ng 1, tapos masusundan siya ng C. And then, everything else will be unchanged. Tama? Kasi mamumultiply ito ng C, so 0, 0, 0, ito ay magiging C, 0, 0, 0, i-add ko to sa kth row, so magkakaroon lang ako ng 1C. So every row translator only alters exactly one entry in the identity matrix. And that's more than that. It alters only one off-diagonal entry. Kasi yung elementary matrix para sa row translator ay may diagonal pa rin na 1 kasi hindi nababago ng row translators yung diagonal entries, right? Tapos nagkakaroon ka lang ng isa pang non-zero entry which represents the scalar multiplier to the lth row. At alin yung nababago? Nandun siya sa kth row and lth column. So meaning, the elementary matrix corresponding to this row translator is the identity matrix except that the entry on the kth row and the lth row ay replaced by the scalar multiplier doon sa ating row operation. Okay? So mas madali siya ngayong i-visualize. Hindi nyo kailangan pa ulit-ulit gawin yung elementary row operation kasi ito yung pattern. Alright? So, napapalitan lang yung kth row, yung entry sa kth row at lth row ng identity matrix by the scalar multiplier dun sa row translator. Okay? So, with that said, so ibig sabihin, kailangan natin mag-develop ng mas madaling paraan para makuha yung LU factorization. Actually, mamaya may bibigay pa akong shortcut. Pero tingnan muna natin kung nasa-satisfy ba yung mga pangarap ko kanina na properties para yung inverse ng product ng mga elementary matrices ay maging lower triangular. Okay? Unang statement dito, Theorem 7.1, elementary matrices are invertible. Actually, yung proof ng invertibility nito ay madali lang because what we want to do is to find a matrix na pwede kong i-multiply sa isang elementary matrix to make it the identity matrix, right? And then do you have any idea how can I do that? Or in essence, paano ko maprove yung Theorem 7.1 na invertible lahat ng elementary matrices? Sige nga, ideas? Tingnan ko kung sinulat ko yung proof. Hindi ko naman sinulat yung proof. Or masyado bang obvious na yung elementary matrix ay invertible? Masyado daw madali, sabi ni Ben Paul. So hindi ko na siya pwedeng ipa-problem set. Okay, so basically, just for those who are not familiar with the rigor of proving, so sige, pakita ko na lang yung proof to save some time dun sa Theorem 7.3. Tapos hopefully when we do the proof for Theorem 7.3, mas makikita nyo na kung paano gawin yung proof ng 7.1. Okay? Kasi mas madali yung 7.1 kaysa 7.3. Now, so let's skip the proof for now. So siguro, pag-isipan nyo, baka ipa-problem set ko yung proof niya. Theorem 7.2 naman, the product of two unit lower triangular matrices is also unit lower triangular. So, recall, pag sinabi nating unit lower triangular matrix, isa siyang lower triangular matrix ng entry sa diagonal ay puro 1. Okay? So meaning, if I have a lower triangular matrix, ang itsura niya ay ganito. 1 yung diagonal, tapos lower triangular siya, so 0 dapat yung nasa upper triangle, upper triangle, tapos dito ay meron tayong mga other entries. So meron tayo dito other entries, so A21, A31, A32, and so on. Ano kayang notation para sa mga non-zero? Sulat ko na lang na C para ibig sabihin may mga non-zero constants possibly dun sa lower triangle. Okay? So meron akong C. Tapos, kumuha pa ako ng isang unit lower triangular. So isa pang matrix na unit lower triangular. Tapos, so 0 siya sa ibabaw ng diagonal, tapos posibleng may non-zero entries dun sa ilalim ng diagonal. And then, ang sabi ng Theorem 7.2, which I think can be proven using exhaustive multiplication, ay unit lower triangular pa rin daw. So if you perform this matrix multiplication, makukuha pa rin natin na isang lower triangular matrix. Okay? Isang unit lower triangular matrix. So, I think okay pa to so far para sa atin, right? Kasi in the end, gusto ko magkaroon ako ng mga lower triangular matrices. Okay? Now, if we tie this up to the general scheme that we are trying to paint, kung makita nyo dito, gusto ko ito sana ay, oops, binura ko ba? Yeah. So gusto ko ay makakuha ng lower triangular matrix. So I'm hoping that this will end up to be a lower triangular matrix. Tapos pag nag-Gaussian elimination ako, tapos row translation lang yung ginagawa, I can do the row translations in such a way that I perform the row translations starting from the first row pababa sa dulong row. So ibig sabihin, nag-create lang ako gumagamit lang ako ng mga row translators na si K ay binabago ko lamang using yung mga rows sa ibabaw ba o sa baba? Dapat sa ibabaw niya or sa ibaba niya. Tama ba? Gusto ko kasing ma-fix si K. So dapat si K ay mas maliit kesa kay dapat si K mas malaki kay L para maging lower triangular matrix lang to. So I want K to be row number. So row number, dapat ito ay mas maliit sa column number. Tama ba? So para mapunta ako sa lower triangle. Para mapunta ako sa lower triangle ng matrix, dapat ay, or baliktad. Dapat mas mataas yung yung row number kesa sa column number. Tama? Tama, dapat K is greater than L. So ang inisip ko ngayon, dahil ang gusto kong LU factorization, meron akong lower triangular matrix. So ngayon pipiliin ko yung mga row translators na gagamitin ko dun sa Gaussian elimination passes. Dapat ay nag-row translate lang ako ng isang row gamit yung isang row na yung number niya ay masasatisfy to. Dapat ang K ay greater than L. Kasi nga, yung elementary matrix corresponding to a row translator ay kamukhang-kamukha ng identity, pero yung entry on the ith row, on the kth row and lth column ay nababago lang by a constant C. And C will be non-zero. So para makakuha ko ng lower triangular, I am hoping, or I would like to impose the use only of row translators wherein K is greater than L. Okay? So ang pangarap ko ngayon, etong mga, nasaan na yung example ko kanina? Yeah. Etong mga E sub i's, sana lahat sila ay lower unit triangular. Okay? Para etong product nila ay ano pa rin, unit lower triangular. Alright? Kasi yun yung nasa Theorem 7.2. Okay? And then since every one of these are elementary matrices, then they are invertible. Tama? So kasi yun yung theorem 7.1. Lahat ng elementary matrices ay invertible. So invertible silang lahat. Tapos pag minultiply ko in reverse order yung mga inverses nila, makukuha ko yung inverse nung product. Tama? Kasi essentially in the LU factorization, I want to get the inverse of the products. So bawat isa ay elementary matrix, bawat isa sa kanila ay invertible. So ibig sabihin EM inverse exists up to E sub 1 inverse exists. So if I take E1 inverse times E2 inverse times E3 inverse hanggang times EM inverse, yun yung yun yung inverse ni E sub M hanggang E sub 1. And I know this to already exist because each of the inverses also exists. Right? So, isa na lamang yung hindi natutupad dun sa wishlist ko. Sana ito ay lower upper triangular. Sana siya ay lower triangular din. Kasi if that happens to be lower triangular, ito na yung LU factorization natin. Si L ay yung inverse ng product ng mga elementary matrices coming from row translations. Tapos si U yung upper triangular matrix na nanggaling doon sa elimination pass. Okay? And then the answer to that is given in theorem 7.3. It says that the inverse of a unit lower triangular elementary matrix is also a unit lower triangular elementary matrix. So hindi pa pala ito yung talagang pinakagusto ko, no? Kasi may isa pang level to it. Pero let's see, before we analyze the implications of theorem 7.3, let's quickly look at the proof, okay? So gusto kong ipakita ng inverse ng isang unit lower triangular matrix ay unit lower triangular elementary matrix din. Ang daming nangyayari, no? So, triangular matrix. So, sasabi niya lang ang inverse ng isang lower triangular elementary matrix ay lower triangular elementary matrix din. And this will give you an idea of how to prove theorem 7.1. So, nangyari dito ay, okay. So, dahil let's consider a unit lower triangular elementary matrix E. Okay. So, kung meron ka ng unit lower triangular elementary matrix E, ibig sabihin si E ay nanggaling sa identity matrix coming from row translation. Okay? With K is greater than L. So, pagpalagay natin na yung elementary row operation na yun ay RK replaced by RK plus CRL. Okay? Tapos ang condition K greater than L, para dun lang siya nangyari or para lower triangular yung makukuha natin. Unit lower triangular pa rin naman yung makukuha natin. And this is the only way that I can get a unit lower triangular elementary matrix, because the two other elementary row operations will not necessarily result to a unit lower triangular elementary matrix. Kaya yung proof pwede ko nang i-limit dito sa case na to. Okay? And then to find the inverse of E, kailangan lang nating i-undo yung ginawa ng ERO. Kasi nga yung ERO ay nag-act sa identity matrix, kaya natin nakuha si E. So para makuha ko kung ano dapat yung i-multiply ko kay E para makuha yung identity matrix, I only need to undo this operation. Okay? Now, undoing this row operation will give us this. So parang ipa-perform ko lang yung inverse nito doon naman kay E para makabalik ako doon sa identity. Okay? So that means kung before I replace the kth row by RK plus CRL, para ma-undo ko yung operation, ang gagawin ko yung kth row nung matrix E ay papalitan ko ng RK minus the multiple of RL. So I will get back to the identity matrix. Okay? And then, dahil gusto kong mahanap yung inverse para ma-prove na siya ay lower unit triangular pa rin, so kailangan ko makita ano yung matrix representation ng elementary row operation. Okay? So to get that elementary row operation, i-apply ko itong inverse operation doon sa identity matrix. Makukuha ko yung elementary matrix F that represents the ERO that can undo what happened in the row translation. Okay? So, kumbaga, mangyayari, dahil alam ko na si IN, kapag ka pinorform ko ito, makakarating ako kay E, pero pag pinorform ko tong operations sa baba kay E, makakarating ako sa IN, so this will give me back the identity matrix. Okay? And so, ibig sabihin naman dito, so ibig sabihin, in matrix form, magiging ano to, magiging, ito yung input matrix, times the first row operation that we perform. So, tawagin nating E. Tinawag ko yatang E yung elementary row operation sa kanya. Tapos, ito naman, it's represented by the matrix F. Tapos, ito ay equal pa rin kay identity. Okay? And then, F is an elementary matrix. So, it is invertible coming from theorem 7.1. So, pwede kong i-apply yung F inverse o i-multiply both sides by F inverse. So we will get E equals F inverse. So ibig sabihin, baliktad pala, no? Kailangan gusto ko makuha yung inverse ni E. So doing it the other way around, so maging FE equals identity muna yan. And then I apply E inverse to the right of both sides. So we'll get, F inverse. Tama ba? Ano ang inano ko F inverse? Gusto ko magka-E inverse. So maging E inverse ay equal kay E inverse. So ibig sabihin si F ay equal kay E inverse. So ang inverse ni E ay yung matrix F that is obtained by simply undoing the elementary row operation that gave us the matrix E. Right? Tapos alam natin si F ay isa lamang resulta ng row translation. So si F ay isang unit lower triangular matrix. So we started with the unit lower triangular matrix E. Yung inverse niya na si F ay lower unit triangular matrix din. Okay? So and then you can devise a simpler proof para ma-prove yung theorem 7.1, and then theorem 7.2 is highly mechanical. So I think I can leave that to you guys, okay? So ngayon, balik tayo dun sa factorization method na gusto natin. So meron na ako nito. So ito yung nanggaling sa row operation. Alam ko, bawat isa sa kanila ay mga elementary matrices. So bawat elementary matrix ay invertible. Kunin ko yung product ng mga inverse nila in the reverse order. I'm gonna get the inverse of the product. So makukuha ko ito. Alright? Tapos, gusto ko ngayong makita lower triangular ba ito. Alright? So, use the property of the inverse of a product. Susulat ko siya isa-isa na ganito. Tapos, ito ay unit lower triangular. Ito ay unit lower triangular din. Ito ay unit lower triangular din. Unit lower triangular din. Kasi yung kanilang inverse o yung pinanggalingan nila ay unit lower triangular din. And then, we are taking the product of lower triangular matrices. By theorem 7.1, this is still lower triangular. Okay? So, hindi na nga lang siya elementary matrix kasi etong matrix L ay hindi na nanggaling sa isang row operation. Ang definition natin ng elementary matrix dapat na-obtain natin by only one row operation on the identity matrix. Okay? But nevertheless, the matrix L representing this product is essentially lower triangular. And that suffices our purpose of finding a lower unit triangular matrix A. Okay? Is that clear? Any questions so far before we go to the examples? Or masyado bang mathematical yung treatment? But anyway, that's okay. Then let's look at a couple of examples. Hanap daw tayo ng LU factorization para dito sa matrix na to. 2, 5, 3, 3, 1, negative 2, negative 2, 2, negative 1, 2, 1. At least for now, you can write on our discussion before to get how to do the hand solution para dito sa example 7.5. So ang gagawin ko lang, Gaussian elimination, usual row reduction algorithm. But this time, I'm gonna take note of the row translators na ginamit ko. Alright? So, wala akong gagawin sa first row. Hindi na ako nag-interchange ng row, so I can leave it there. And then now, I want to eliminate the 3 here kasi gusto kong maging 0 yung nasa ilalim. Kasi ang goal natin dito, mahanap yung upper triangular matrix. So this should vanish. Dapat mag-0 yan. So you need to think of what should be the multiplier to the first row in order to eliminate the 3 here. Okay? So in that particular case, I want to multiply the first row by -3 halves. Para -3 halves times 2, -3 plus 3. Oops, yes, mag-0 na ito. But you need also to do that for all of the entries in the remaining row, in the remaining columns. So pag ginawa mo yun, you replace the second row by the second row minus 3 halves of R1, you'll get this one. Okay, which is going there. Palapit na siya sa upper triangular form kasi dito 0 na yung kanyang entry. Okay? Then you do the same thing for the third row, you'll get this, and the multiplier that I want is 1/2. Okay, 1/2 kasi ng first row. So si third row, mapapalitan ng third row plus half the first row. So half the first row is, or the entry here in the first row is 1 plus -1, 0. Half of this is 5 halves plus 2, so that's gonna be 9 halves. Makukuha ko to hanggang kay 5 halves. Okay? Tapos, ang problema ko na lang to have an upper triangular matrix is this 9/2. Pero ang gagamitin ko to eliminate the 9/2 here ay itong nasa second row. Kasi hindi ko pwedeng gamitin yung first column, di ba? Kasi pag ginamit kong pang row translate yung first row, mababago itong 0 na to. Kasi may non-zero entry rito, idadagdag ko rito, magiging non-zero siya. Kaya restrained ako na gamitan lamang tong middle row. Para magawa ko yung elimination dito and then hindi mabago yung mga zeros na nandito sa first row o sa first column. Okay? And then it happens that what I need to multiply the second row with para makuha yung pandagdag dun sa third row ay 9/13. Tapos ito na, medyo fractional na yung mga nangyari. And then we do this until we come up with the upper triangle here. Okay? Tapos ngayon, i-build ko yung LU factorization. Now, ang gagawin ko, kukunin ko lamang yung elementary matrix that corresponds to the row translations that we did. Remember, the first row translation that we did is this guy. Okay? Tapos nalaman natin by a remark earlier, identity matrix lang yan. Pero papalitan ko yung nasa second row and first column ng identity matrix by -3 halves. Kasi ang C natin dito ay -3 halves. So now, dun sa elementary matrix for the first row translator, it's the identity matrix except that the entry on the second row first column ay equal kay -3 halves. Right? Again, that second row first column ay magiging -3 halves. And that's what I got here. Okay? Second elementary matrix, identity matrix pa rin, pero yung entry sa third row, first column, ay equal kay 1/2. And that's what we have here. And that's also true for E3. Okay? Tapos i-assemble ko na ngayon. Ano yung lower triangular matrix L? Basically, it is the product of the inverses of the E sub i's. So it should be E sub 1 inverse times E sub 2 inverse times E sub 3 inverse. Madali lang i-invert yung mga elementary matrices natin na nanggaling sa row translators kasi sila ay heavily sparse. Ibig sabihin, ang daming zeros dun sa matrix na yun. And usually, it's very cheap to compute the inverse of sparse matrices. And actually, you can deduce from the proof of theorem 7.3 kung anong itsura noong inverse ng mga elementary matrices na yan. Okay? So if you're patient enough, you do the multiplication, you will get this as our product. And essentially, here we go. We got the LU factorization, a lower unit triangular matrix, times an upper triangular matrix. So this is one of the LU factorizations of the matrix A. Okay. Kailan medyo matrabaho to kasi ang nangyari ay, ang ginagawa ay kailangan kong i-track down pala bawat isang elementary matrix. Tapos, pag na-track down ko na bawat isang elementary row operation, kailangan kunin yung kanyang elementary matrix. Tapos gagawin ko, i-invert ko yung elementary matrices. Pag multiplyan sila in the right order, saka ko pala mahanap yung lower triangular matrix. So it seems to be a handful of careful steps para makuha si matrix L. Pero meron tayong pwedeng magawang shortcut. Okay? Now, this shortcut gives me ano yung itsura ni matrix L without doing the inversion and multiplication of the elementary matrices. So, ibig sabihin daw, yung lower triangular matrix, the lower unit triangular matrix, para dun sa LU decomposition, doing our method, ay equal lamang sa matrix na 1 yung mga nasa lower triangular, tapos 0 siya everywhere, pero yung entry niya on the ith row and the jth column, provided that I is greater than j to ensure yung pagiging lower triangular niya, ito ay equal doon sa multipliers doon sa row translation. Okay? So ibig sabihin pala, kailangan ko na lang i-track down kung ano yung mga constants na kailangan kong gamitin sa row translation. Okay? Tapos, kung ano man sila, gagawin ko na lang ay ipoposition siya in doon sa matrix L. Pero medyo may problema pa rin itong method na to kasi wala tayong shortcut para dun sa matrix U. And then sort of you also need to keep track of everything. All right, of all these coefficients. Kaya ito yung drawback nito. Madali siyang intindihin yung idea ng LU factorization using this approach, pero mahirap talaga siyang i-implement. Kasi kailangan mo tingnan step by step kung ano yung nangyayari dun sa Gaussian elimination pass. Pero essentially, halimbawa dito, okay, kung kukunin ko yung LU factorization ng 4x4 matrix na to, okay, gagawin ko lang ay yung alam ko na yung lower triangular matrix, ang laman niya ay yung lower triangular matrix ay unit. So ibig sabihin 1 lahat ng nasa diagonals niya. Okay, kasi ito yung L natin. Yung L na nakukuha natin in my procedure here is a unit lower triangular matrix. Tapos zeros na siya elsewhere. Okay? Tapos, titingnan ko ngayon, ano yung mga entries dun sa lower triangle? Okay. So, sabi nitong remark na to, siya lamang yung negative, ano ba yung negative? Siya ay kung ano yung pinang-multiply ko kay row J para bago i-add yung multiple na yon kay row I. So, let's look at a particular example here. So say I'm on the first elimination pass. I want to eliminate or I want to eliminate this entry para papunta na siyang upper triangular kasi gusto ko maging 0 yung 5 na yon. And how do I obtain that? Alam ko na kailangan ko ng row translation. Anong row translation? I need to multiply the first row by negative 5 halves. Tapos i-add to dun sa second row para mag-0 ito. Right? So, kailangan mag-multiply ako ng negative 5 halves dito kay 5. Right? So, ibig sabihin, kung babalikan ko dito, ang row operation na kailangan ko, dapat si R2 ay maging, so ito ay R2, becoming R2 minus 5 halves ni R1. So, itong remark na to tells me that the entry of L on the second row and the first column must be equal to 5/2. Okay? Kasi dapat itong C na to, yung subtrahend o yung scalar dito sa Ri minus CRJ, siya si Mij. So again, in this particular example, alam natin na si row 2 dapat mapalitan ng row 2 minus 5 halves ng row 1. So ibig sabihin kay matrix L, yung lower triangular matrix natin, ang entry niya on the second row, first column, so second row galing dyan, first column galing doon, ay equal dapat kay 5/2. Okay, which is that guy. Okay? And that's what you see here. 5/2 na siya. And then here, I need to eliminate the 3. I will be using 2 to do that, so I need to multiply the first row by -3/2. Never mind the negative. So yung entry dito dapat ay 3/2. And then same thing goes for this guy. Dito naman, para ito ay maging 0, kailangan kong i-multiply si first row by 1/2. So ibig sabihin, ang row translation ko ay R4 ay papalitan ng R4 minus -1/2 R1. So ang entry ko rito sa fourth row, first column ay si -1/2. Okay. Tapos, kailangan makita ano yung itsura ng matrix after doon para makuha naman yung mga entries na nandito. Pero you can think of shortcuts on how to do that. Kasi parang dito, kaya mong i-program yung unang pass kasi kailangan mo lang naman yung quotient. The quotient between this guy, this divided by that. Alright? So, para makuha mo yung mga entries. So, madali siyang i-figure out or i-program. Tapos, ang meron ka pa lang, ito ay 0 pa rin, ito ay 0 pa rin, ito ay 0 pa rin, para malaman kung ano yung magiging itsura nito after doing the first 3 row translations, pwede mong i-pre-multiply ito by this guy. Puro zeros pa to. Para makuha mo yung sagot dun sa first pass. Tapos pag nakita mo na, alam mo na yung itsura ng second pass, kaya mo na ngayong i-harvest ano yung mga magiging entry nito. Bakit siya naging 1? Bakit siya -1/13? Okay. So, ang ibig sabihin, ito na lang yung magiging kulang. So far, 0 pa lang siya. I-multiply mo uli itong matrix na to that you have so far by the matrix A para makuha ko ano yung itsura nung magiging product. Okay? And essentially, we get this. Tapos para makuha, madali ba makuha yung A inverse? Tapos para makuha ito, alright, either tapusin mo yung row operation o kaya gamitin mo yung property ng inverses. And I will let you think about that. So kung paano siya ipoprogram ng convenient. Okay? Pero I hope the process makes sense, especially if you're doing it by hand. Madali siyang gawin kasi gagawin mo lang naman yung elementary row operations, tapos makukuha mo si U, tapos i-assemble mo lang yung L in a nice way. Okay, so this is an LU factorization. Now, paano nagiging helpful yung LU factorization dun sa computation ng isang, say, iterative system? Again, yung reklamo natin before, pag meron kang AX equals B upper J, kailangan mo itong isolve, tapos yung mga B upper J's ay hindi laging available right away. Kailangan mo ba mag-Gaussian elimination every time para lang makompute yung solution X dun sa system? And the promise of the LU factorization ay hindi mo kailangan tong gawin paulit-ulit. Kasi ang kailangan mo na lang gamitin, kailangan mo na lang gawin ay back substitution na lamang kasi hindi mo na kailangang i-redo yung reduction into an LU system or into Gaussian, into row echelon form. Or hindi row echelon form, into row reduced form. Okay? So tingnan natin, ano yung idea dun sa pag-solve ng system? So nag-start tayo sa AX equals B. Tapos kumuha tayo ng LU factorization ni matrix A. So the matrix A was replaced by LU here. And then I will appeal to the associative property of matrix multiplication. So I will group U and X first before multiplying or left multiplying the answer by L. So ito yung mangyari. Kakaroon na ng L times UX equals B. And then I'll have a change in variable. I will let Y to be, hindi to U sub X, ito yung isa sa mga typo, dapat ito ay UX. So itong UX na yan, papalitan ko lang siya ng Y. So essentially, I'll be solving the system LY equals B. Ayan pala, sinulat ko siya. Pero maganda sa LY equals B, madali kasi siyang isolve kasi lower triangular na yung matrix L. Pwede ka nang mag-forward substitution. Paano yung forward substitution? Kasi, halimbawa, meron kang LY equals B. Si L ay lower triangular. 1, 1, 1. So ito ay 0. Lower triangular siya, no? So dito ay may mga constants. Tapos ito ay puro 0. Tapos meron kang Y1, Y2, hanggang Yn. Tapos ito ay equal kay B1 hanggang Bn. Okay. So, una mong equation dito, when you carry out the multiplication, this guy times that guy, so magkakaroon ka kagad ng y1 equals b1. Tapos na yung boxing for y1. Alam mo na kung ano yung itsura ni y1. And then you do forward substitution. Bakit siya forward substitution? Kasi in this particular case, remember may entry dito. Tawagin natin tong L21. Okay? So, susunod naman sa second row. Multiply them. L21 times this guy. Pinerform ko yung matrix multiplication. I'll get what? I'll get L21 y1 plus y2 equals b2. All right? However, we already know y1. So we will substitute the value that we found for y1 into the equation that we got by moving forward along the rows. Kaya siya forward substitution. Alam ko na yung y1. So ibig sabihin ngayon, gagawin ko na lang L21 times b1 plus y2 equals b2. And then I'll just transpose this guy dun sa kabila. Oops, naiwan pala yung minus. So ito na yung value ni... Ito ay b1. Ito na yung value ni y2. And then, susunod, magfa-forward sub ka na naman para dun sa third equation, you will get L31 times y1 plus L32 y2 plus y3 equals b3. Tama ba? Multiply. So, andito naman ako sa L31, L32. Multiply ko siya dito. So, L31 gets multiplied by y1, L32 gets multiplied by y2, 1 got multiplied by y3. So I get this guy equal kay b3. And then I can solve for y3 by substituting previously computed y1s and y2. Alright? So mga kompleto ko ngayon, ano yung itsura ng mga y1s at saka mga y2. So essentially, I'm not doing anything new here. Madali actually i-program ito into a serial loop. Alright? So isa lang siyang mabilis na for loop starting from 1 hanggang n, hanggang makarating ka sa dulo. So serial yung computation niya lamang. Makukuha mo na yung mga values ni y. Para ma-compute yung values ng original variable x, magba-back substitution naman ako dun sa natitirang equation. Because remember, we can solve for y by looking at the equation ly equals b. Pero ang sinusolve talaga natin ay ax equals b. So essentially, ang natitira pa ay ano yung letting statement natin. Ang statement natin, si ly ay equal kay b. Kailangan kong bumalik kay x. Pero si y, hold on, paano ko siya gagawin? Yeah, ux will be equal to y. Because, bakit siya yung mangyayari? Alam ko na yung values ni y. Yeah. Kasi si ux ay equal kay y. Ito yung hinahanap ko. Si y ay equal kay ux. Alam ko na yung mga values ni y, mga constants na lang yan. Nanggaling niya siya sa pag-solve ng ly equals b. So solve ko na lang yung ux equals y. This time the y's are now known constants. And this is nice because I can use back substitution for it. Bakit naman back substitution? Kasi ang itsura nung u, siya ay upper triangular. So 1, 1, 1, 1, 0 siya dyan. Tapos posibleng may non-zero entries dito. This is u23, u24, and this is u... Kulang yung aking rows and columns, but this is essentially u... Ito ay 3, 3, so ito ay 3, 4. Okay, and so on. And then I have unknown x1, unknown x2 hanggang xn. Tapos ngayon ay equal kay y1 hanggang kay yn, the values of which were already determined before. Okay? Back substitution siya kasi doon ka naman sa ilalim manggagaling. If you multiply the last row by the vector of unknowns, we will get xn equals yn. Yn is already known previously, so tapos na tayo dyan. Alam na natin yung constant value ni xn. And then we move backward, pataas. So ito naman, yung second to the last row times this guy. So we'll have what? We'll have xn minus 1 plus yung entry ng upper triangular matrix previous row na. So that's gonna be n minus 1 comma n times x sub n minus 1 ay equal dapat kay y sub n minus 1. Tama ba? So yung diagonal entry na UNN, ito ay mamumultiply dito sa u sub n minus 1. Ito ay 1. So x sub n minus 1. Tapos yung entry dito ay u sub n minus 1 comma n. Mamumultiply siya ng xn. So dapat ito ay xn equals that guy. Right? Tapos back substitution kasi alam na natin yung value ni xn. Si xn ay equal kay yn. So this guy is just yn. Tapos ngayon, si y sub n minus 1 ay given. So kaya nating isolve for xn easily. Alright? So pwede pa rin i-serialize yung process, do it in a for loop, but your for loop will start with I equals n. Tapos ang increment mo ay -1 hanggang makarating ka sa I equals 1. Okay. And then, itong system na to, hindi na siya nakadepende with the interrelationship between the variables, right? Kailangan mo lang malaman ano yung right-hand side B. Pag na-factor mo na si L, pag na-factor mo na si A via LU factorization, meron ka lang dalawang system na isosolve. One via forward substitution, which is this one, and then isang back substitution by solving this equation. Naka-serial din yung pagko-compute nito. Solve mo muna si y's bago ma-solve yung mga x's. Pero ang maganda sa kanila, hindi ka na mag-Gaussian elimination kasi nagawa na natin yung Gaussian elimination dun sa mismong factorization process. Okay? Now, I trust that you can read through example 7.6. Okay? Para dun sa LU factorization. Tapos may example din dyan ng back substitution. If you want to retrace everything. So, step by step ko naman dyang sinolve. Kasi makikita nyo na, okay, nasa example 7.6, yung pagsosolve ng isang particular linear system. Pero, paano kung halimbawa nabago na to, naging 2, instead of 2, -3, 5, 7, yung bagong set of data mo namang nakuha ay, say, 1, 1, 1, this should be 1, okay? Hindi mo kailangan mag-Gaussian elimination uli. Hindi mo kailangan hanapin yung inverse ni A kasi nga mahal yung inverse ni A. So pwede ka na lang uling mag-forward substitution using the matrix L and then backward substitution using the matrix U na nakuha nyo na sa LU factorization. Okay? And this will give us an efficient way ng pagsasolve ng mga systems of the form AX equals B, dapat upper K, K going from 1 to M, where each of the right-hand side vectors B sub K is not readily available at all time steps. Okay? Now, dahil wala ng oras, ang bagal ko talaga magturo, no? Siguro next time bibilisan ko na. Lalo na kasi pagka hindi ko kayo nakikita. So, hindi ko alam kung nabobore na kayo sa sobrang dami ng sobrang dali nung ginagawa. So baka tinitreat ko kayo as mga super bata. Sabihin nyo na ako pag masyadong mabagal. Pero I think I can give you as reading assignment pages 14 to 18. Oo nga eh. So problema ko yan, Ben Paul. Masyado akong detailed detailed mag-discuss. And that is sometimes a disadvantage. I don't know if that's a disadvantage for you guys. Pero I hope that with the detailed discussion we did in the majority of the module, ay kaya nyo nang aralin yung natitirang parts ng module na hindi ko na maaabot due to time constraints. Kesa kasi ang pilosopiya ko kasi kesa tapusin ko lahat, i-detalye ko na lang yung discussion for the crux of the module, tas kayo na lang yung bahalang mag-figure out nung natitira. Okay? I hope that works for you, but if not, then just let me know. Yeah, please read through the rest of the module because here I discuss an alternative way on how to do this. Ito na yung mas mechanical na definition. I hope you can go through this part. So this discusses the Doolittle factorization and the crowd factorization. Pinagkaiba lang naman nila sino yung upper at saka sino yung lower, sino yung unit triangular matrix. Dun sa Doolittle factorization na ginawa natin kanina, meron tayong lower unit triangular matrix. Ibig sabihin, ang L natin na nakukuha ay 1 yung yung diagonal entries, lower siya dapat, no? So baliktad. Lower triangular times an upper triangular matrix. Wala tayong pakialam kung anong itsura ng upper triangular, basta yung nakukuha nating lower triangular matrix 1, yung main diagonal. The set of all matrices is not a unique factorization domain. So posible na meron kang isang matrix na may iba't ibang klase ng factorization. At nangyayari yon sa LU factorization. There could be more than one way to LU factorize a matrix. Isa pa lang yung na-discuss natin, yun yung Doolittle. At ang particular case ng Doolittle factorization ay meron kang unit lower triangular matrix. So to mirror this, pwede kaya nang gawin naman nating unit triangular matrix ay yung upper triangular matrix U. If you do that, ang makukuha mo naman ay yung tinatawag natin na Kraut factorization. Okay? Yun yung etong form naman na ito. Tapos ito yung diniscuss ko in a more algebraic way than the conceptual way as we did or the more abstract way that we did Doolittle factorization. Kasi sa Kraut factorization, ng idea naman, meron akong matrix A, gusto ko siyang kunan ng LU factorization in a Kraut fashion, okay? Pero kay Kraut kasi, meron kang lower triangular, no restrictions on it. Nakalimutan ng student ko yung backslash, so dapat curly L siya. Tapos, yung upper triangular matrix niya, siya yung unit. Okay, 1 yung main diagonals niya. So, pwede nyo itong gawin. I think there is a version of the column operations para makuha to using the method that we did side by side with Doolittle's. Pero ngayon, ginawa ko naman to give students a different flavor ay maging ano naman siya, maging mechanical. Okay? Paano siya naging mechanical? Alam ko na yung gusto kong forma noong factorization. Given yung matrix na fina-factorize ko, right? So, paano ko siya gagawin? Algebraically, I'll take advantage of the fact that maraming zeros dito. Alright? So, pag nag-multiply ako, pag kinary out ko yung matrix multiplication, maraming zeros dito. So, ibig sabihin ko, konting constants yung kailangan ko. So, ang idea dito sa Kraut factorization, gusto ko mahanap yung mga L's at saka yung mga U's na entry without using the same ERO's pattern na ginawa natin last time. Although you can also derive Kraut factorization using that way. Pero ito, ibang flavor naman tong kay Kraut. And conversely, you can derive the Doolittle factorization using itong method na gagamitin ko kay Kraut. Okay? So, paano yung idea? Ganito lang. Carry out the matrix multiplication. So, halimbawa, ito muna. This guy, dot product with this guy, makukuha ko yung first entry nung matrix A. But this will only tell us L11 times 1, which is L11, ay equal kay A11. So, ito ay check na to. Na-compute na natin siya. It's just equal to A11. Okay? And then, ano yung pwede kong susunod na gawin? Pwede namang ito. Second row times this guy. That product with this guy. Ang makukuha ko naman na sagot dyan ay si A21. Alright? Pero this dot product, puro zeros. Remember yung nandito? Kasi upper triangular matrix siya. So, matitira lang dito ay L21 equals A21. And that will happen for all rows. So, in general, the entries in the lower triangular matrix will just be the entries of the first column. Okay, so ito, siya yung magiging first column nun. So, ibig sabihin, parang nagbibingo ka rito eh. So, alam ko na to, alam ko na to, alam ko na silang lahat. Similarly, pwede ko rin gawin yung same pattern, pero this time, anong susunod kong gagawin? First row daw, kaya kong ma-determine yung first row. Paano ko ma-determine yung first row neto? I'll take advantage naman ng maraming zeros ito. Marami siyang zeros. Pwede ko siyang i-multiply dito. Ibig sabihin, U21 times L11 ay equal kay A12. Tama ba? Yes, maging equal siya kay A12. Tapos ito naman, this guy, ito yung medyo may komplikasyon na. Kasi hindi pa rin. Kasi ito ay magiging L11 U13 ay equal kay A23. So essentially, makukuha ko naman ng madali itong mga nasa first row na ni matrix U. Okay? So kaya ito yung mga formulas para doon. Provided that L11 is not equal to 0. Tapos gagamitin ko itong mga known values para ma-determine ano naman yung nandito, ano yung nandito, tapos gagamitin ko siya kung ano yung nandito, and so on, hanggang makakome up ako ng formula na to. So what I want you to read or verify na tama ito. Para makita nyo yung factorization idea. And probably the first item on my side of the problem sets is for you to do the similar routine para sa Doolittle factorization. Okay? So ito yung method kay Kraut. Ito yung approach kay Kraut. I want you to mirror this process para makuha naman yung similar idea para sa Doolittle factorization naman. Kasi itong approach na to, ang binigay niya sa atin ay Kraut. Gusto ko ipagawa sa inyo in the first problem set ay gawin niyo yung para sa Doolittle. Pwede niyo i-pattern yung discussion dito sa paragraph na ito. Okay, just to give you sort of a mechanical exercise for now. So kasi numerical linear algebra naman tong course, so medyo technical siya talaga. So para rin ma-practice kayo magpag-work sa matrices. Okay? I'll give you a formal statement of that first item in the problem set siguro later tonight or early tomorrow. Okay, okay lang ba yun? And then ang deadline ay, kailan tayo nagde-deadline? End na ba ng SEM? Tama nga ba? Yun ang huli naming usap ni Sir Joms.
Sir, yung mga kay Sir Joms, may mga malapit na deadlines pero hindi strict kasi sabi niya pang tulong lang sa amin pero yung talagang deadline ay yung sa dulo.
Okay, yeah. So sa dulo na lang din yung deadline pero ilagay niyo na sa portfolio kayo naglalagay, no? Lagay niyo na sa portfolio niyo yung discussion once you have done this, and then send me an email tapos para i-check ko na siya para makomentan ko tapos ma-improve niyo siya if kailangan ng improvement, So that would be your first problem set, and then reading assignment na lang din yung natitira. Actually, it's just some examples after. Okay? And then announcement, I will not be available on Friday. Merong strat planning ang graduate school at pinapa-attend ako doon. So I'll be out of town on Friday. Pero in lieu of our class, may papapanood na lang ako sa inyong video about QR decomposition. All right? Yun yung nandun sa second module or second PDF na in-upload ko. It's another factorization method, pero hindi naman siya LU, siya ay QR factorization, meaning it's writing A as a product of a unitary matrix Q and a rectangular matrix. Rectangular matrix nga ba yung R? I think R is either an upper triangular or a lower triangular matrix. Depende dun sa pagkakadiscuss. So yeah, i-share ko na lang yung kailangan yung panoorin na video kasama nung statement nung problem set number 1 sa akin. All right? So yun na lang yung gawin nyo sa Friday. Okay? Panoorin na lang yung video. All right. Any questions? All right. So kung wala na guys, thank you for coming today and enjoy the rest of the night, and we'll see each other siguro next week na. But feel free to send me an email or a chat whenever you have some questions. All right? Bye guys.
Thank you, sir.
Sir, thank you.
Thank you po, sir.
All right.